Good evening. Welcome to the session organized by the Computer Science and Information Technology section of Sri Lanka Association of Advancement of Science. Today, our resource person is Dr. R.H.P.D. Silva. He is a senior lecturer attached to the Department of Mathematics of the University of Sri Javadhanapura. Without further introduction, I would like to invite Dr. Silva to conduct this session. Over to you, Dr. Silva.
Okay, thank you. Good evening. Thank you for giving me the opportunity and organizing this session. Can you give me the permission to screen share?
Yes, now you have. Sorry for that.
Thank you. Okay. So historically, logic programming based on non-monotonic logic was considered to be. Sorry, can you hear me clearly or any disturbances?
Yes, I can hear you clearly.
Okay, thank you. So historically, non-monotonic was monotonic logic and logic programming was considered a good option to in knowledge representation, but they run into a problem when they want to handle default reasoning. For example, let's say we are planning our schedule for a week, and if we know that every Tuesday we have a class, normally we assume that there is a class and make our plan. But later, if we found out this class is cancelled, then we can revoke our decisions and allocate something for that time slot, that new free time slot. So in logic, this was a problem because in normal logic, if we have 5 axioms, I cannot add a 6th axiom going against them. Then there is a contradiction. So this is the reason they came up with this non-monotonic logic. This is a one approach to handle that difficulty. Okay, so this ASP is one language developed out of Prolog. Now it's a standalone language, and it has some problem-solving software like Klingo and DLV and Spark. So today I will go over how the basic concept, how to compute answer set for a ASP program. Okay, this one I will say how manually calculate answers for a ASP program. But for this you have solvers, okay, like Klingo and DLV. So first I will go through the basic syntax of the language. Then I will go through informal semantics, formal semantics, and briefly mention some applications. So first of all, I will start by introducing the signature. This is like an alphabet for the language. So it consists of 4 sets, objects, functions, predicates, and variables. So these functions and predicates are associated with a number called RT. That is the number of parameters they will entail. Okay, so this is an example of a domain signature for a small program about a family. So we can see that we have objects, John, Sam, Alice, male and female, and these predicates, father, mother, parent, child, and gender. The RT of predicate is 2, it is clear from the context. Okay, if we want to say John is the father of Sam, we will say father, John, Sam. Okay, then we have these variables in ASP. We use capital letter to represent variables. So here we have 2 variables. Okay, and currently this family set is empty. A function set is empty. I will give an example of a function later. Okay. Also, sometimes we can consider sorted signature. Sorted signatures we divide this object group into different groups. For example, if I want to make a sorted signature for family, I can introduce a sort called person and say John, Sam, and Alice are of that sort, and making gender a sort and tell male, female belongs to that sort. These are like data types. Okay. So if we have sort with functions and parameters, we have to say what type of sort of parameters it will accept. So for a father, I accept a person and a person. So if I want to say John is the father of Sam, I can say father John, Sam. Also, if I look at the predicate gender of, it again accept the sort, two parameters of sort person and gender. Okay, so this is a sorted signature. Okay, so the next thing important is terms. Okay, terms over a signature sigma defined recursively. Okay, variable and object constants are terms, and if T1 to Tn are terms, by passing these terms into a parameter, we get a new sort as a new term. Okay, by passing these terms as object to the function, we get a new term. Okay, so terms containing no symbols for arithmetic function and no variables are called ground terms. Okay, so here again we have the family signature. Here we have the function car. Okay, so here we are assuming each person have exactly one car. So John's car I can label by car John. So it is a new object. Also I can talk of car Sam and car Alice. Those are terms. Okay. Also John, Sam, Alice, male, female are terms. Variable X and Y are terms. So X and Y are non-ground terms. John, Sam, Alice, and car John are examples of uh, terms, the ground terms. Okay. So there is a little problem with this definition. So because if we put a term, input a term into a function, that becomes a term. So according to this definition, car male, car female, car John also becomes objects, terms. Okay. Because term is variable and object contains, and inputting terms into a function, we get terms. So those unwanted terms are also defined as terms under this definition. So when we are programming with an unsorted language, we have to use safety rules in the program to avoid these problems. But if we are using a sorted language, we can get out of that problem just by saying car accept only parameters of type person. Okay, if we use a sorted language, we don't have that problem. So we don't have to use the safety rules. Okay, taken care by the sorting. Okay, now we have this atomic statement. So for a predicate, but to a predicate by inputting terms, we get an atomic statement. Okay, so if T to Tn are terms and P is a predicate of Rtn, I can input these terms into the predicate and build a atomic statement. If the terms in the atomic statement are ground, we call them ground statements. Okay, then the literal is an atom or its negation. Here this negation is the negation from classical logic. Okay, so literal is an atom or its negation. Now a program of ASP consists of a signature and a collection of rules of this form. Okay, this is the body of the rule and this is the head of the rule. So symbol not is a new logical connective called default negation. Not I is read as not believe that I is true. Okay. So this not is a new logical connective. Here disjunction or is also a new connective, sometimes called optimistic disjunction. Okay. So this is read as L1 is believed to be true or L2 is believed to be true. Okay, it's different from the classical disjunction. Okay, I will talk about this not operator later. Okay, with examples. So the left hand side of the rule is called head and right hand side is called the body of the rule. Okay. Head of the rule can be empty, then we call it a constraint. And body of the rule can be empty, then it will look like this, and we call it a fact. Okay, so then I will give the definition of satisfiability. Okay, if S is a set of ground literals, I say it will satisfy a given S is satisfying a given literal L if L belongs to the set S. Okay, and I will say it satisfy a extended literal not L if L does not belong to set S. Okay, then I will say S satisfy disjunction of literals if at least one of them belongs to S. Set of ground S satisfies set of ground extended literal if it satisfy every element of the set. Okay. S satisfy rule if whenever S satisfy body if it is satisfying the head of the rule. Okay. For example, let's look at this set of extended literal E. And if I say pick a ground set of ground literals S1, here to see whether S1 satisfy E, I can check each literal on E. Here P, literal P is satisfied by S1. Okay, because P is in S1. So from rule 1, S1 satisfies P. But it does not satisfy Q according to rule 1 because Q is not in S. So this S1 does not satisfy E according to rule 4 because there is one literal in E that is not satisfied by S1. Okay, if I look at this S2, it satisfies the literal P from 1 because P is in S1. It satisfies the literal Q from 1 because Q is in S2. And also it satisfies the literal not this classical negation with R because that is also in set S2. Okay, but also it satisfies not S from 2 because S is not in S. Okay, so this set S2 satisfy all the literals. Okay, so this S2 satisfy E because it satisfy all the literals according to 4. S2 satisfies E. Then S3 contains S. So according to 2, this S3 is not satisfying not S. So S3 again is not satisfying E. So here I can say S2 satisfies E. Okay. Now I will go and describe the informal semantics. So here we say if the program is given, we associate that program into an answer set. Okay, this answer set is the conclusions rational believer will come if he believes in all the rules of the program. Okay, so to construct this answer set informally, we can use these three rules. First, satisfy rules of phi. That means if believe in the head of a rule, if I believe in the body. Do not believe in contradiction. Adhere to the rationality principle, says believe nothing you are. And use these three to construct answer set. Okay, so I will show you first how to construct answer set for these programs. Okay, so the first one is I have two rules in the program. Here this QA is a fact. Okay, so fact has an empty body. So empty body is uh, satisfied trivially. So because of that, I have to believe in QA. Okay, so I include this QA in my answer set because I'm forced to believe on the fact. Now I am believing on the body of the rule in rule 1. So I have to also believe on head. So answer set for this is QA PA. Okay. Now I look at another rule. Here I have three facts. So my answer set should include those three facts. Okay. Now if I look at the rule 4, the not QA and RA is satisfied by S. Therefore, we have to satisfy the head PA. Also, we have to believe on the head of that rule 4. So I have to include PA in my answer set. But if I go to the rule 3, the RB is not in my answer set. So I am not forced to believe. I am not believing in the body. So I am not forced to believe in PB. So this is my answer set. This answer set satisfies all the rules. Okay, because rule satisfies rule 3, because it doesn't satisfy the body, we don't have to worry about the head. Okay, if I include also PB, still my answer set satisfies all the rule, but then I'm believing on something I am not forced to believe. So because of rationality principle, I am believing on PB. Okay. Do you have any questions up to now, or I'll continue? Okay. So this is another program. Here rule 8 is a fact. I have QA or QB. So here this will be satisfied, or I have to believe in this rule, head of the rule. Here it's a O. So to believe, I am not forced to believe on both of them. I have to believe one. So if I believe one, it will be satisfying this rule with O. Okay. So one option is to believe QA. Okay, so if I believe QA, it is enough. I am believed to the first rule is satisfied. Now, because I am believing QA, I have to include PA in my answer set. Okay. Then QB, I am not believing in QB, so that rule is already taken care of because I am not believing in the body. Okay, so this is one option. And here I am believing on QB from this rule, then also rule 8 is satisfied. If I believe in QB, according to the rule 10, again, I have to believe in PA. So PA is goes into both the answer sets here. Again, here I'm not believing in both of them because of the rationality principle. Okay, I'm not going to believe anything I'm not forced to believe. So if I believe one of them, that statement becomes satisfied. So I don't have to go to believe in the other one. Okay, so this program have two answer sets. Okay, So if I go to this program, here there are no facts. This is the classical negation in the body. So I'm not believing the body of the rule, so I don't have to believe in the head. Okay, so the answer set in this case is empty set. Okay, but it's a valid answer set. Here the answer set is empty set because there are no facts to believe. Also, I am not believing in this body, so I don't have to believe in the head. Okay. Now in this answer set, I can start with the empty set as my answer set because I am not believing in facts. But then that empty set satisfy the body, no? Because PA is not in the set. So that set satisfies the body. So because I am believing in the body, I have to believe in the head here. Okay. So because of that, I have to include QA in my answer set. So this is the answer set for this program with this not. This is called default negation not. Okay, so answer set for this is QA. So if I go into this program, here again, this fact is there. So I have to include that fact in my rule. I have to include the fact here in my answer set. So if the fact, this fact is in my answer set, then I am not going to worry about the rule 14 because the body is the rule is not satisfied by the set because PB is in this set. Therefore, I don't have to, I'm not going to include QB head. But if I go to rule 13, PA is not in this set. So I am believing body is satisfied. So I am believing in the body. I have to include the head. Okay. So for answer for this program is PB and QA. Okay. Now I define the logical entailment for this one. So I say program P entails a literal L if this literal L belongs to all the answer sets. Okay. If this literal L belongs to all the answer set, I'm going to say that this belongs to all the answer set. So if we look at this previous program, we know our answer set for this program are this PAQA and PBQA. So if I look at QA, that belongs to both answer sets. So I say pi entails QA. Okay. Then I will look at another example with this program pi1. So I say not, if not QA, PA. So here for answer set for this is PA, no? Because we are not believing the body, we have to include the head. Okay, because of the not operator. So now I can explain the non-monotonicity of this system. So we can say pi1 entails PA. Okay, pi1 entails PA. I can say pi1 entails PA. Now I construct another program. I have the first rule of the previous program and I add another rule called QA. So now this is extension of the previous program by adding another rule or axiom. So now in this program, answer set is QA, no? Because QA is a fact, I have to include QA. Because I included QA, I'm not going to include PA, no? Because I'm not believing in the body now. Okay, body is not satisfied, so I don't have to include the head. Okay. Now, phi2 entails QA. Okay. Now we can see previously program entailed PA, but I add another axiom, then it recall its previous conclusion and come up with a new one. Okay, so this is why we call this is non-monotonic. In normal mathematical logic, this is not possible. If I have set of axioms, I come up with a decision, some conclusion based on those axioms. Adding a new axiom cannot change the previous one. We can maybe come up with new conclusions, but it will not recall the previous conclusions. Okay. So that is important for mathematics, because if we prove a theorem, it remains proved, no? Unless there is a mistake, so it remains proved. Even we add more axioms, it will not change our previous conclusion. Okay. We can take this further. Again, if we look at this program, now this program entails not QA, because not QA is not in my set. I have to include this head, not QA. Okay, so this only answer set is not contains not QA. Because of that, pi1 entails not QA. Again, if I add the rule QA for this program, now my answer set is QA, no, containing this fact. So program entails QA. So by adding another axiom, my conclusion is going against the previous one, completely the classical negation of the previous conclusion. Okay, this is possible because this is non-monotonic logic. It's based on non-monotonic logics. Okay. Then I will say how these programs going to answer queries. Okay. Answer to a ground conjunctive query. This AND is the normal logical AND. Okay. We answer yes if pi entails all the literals in the conjunction. I say no if there is at least one literal. If it entails negation, this is classical negation of one of these literals, then I will answer no. I will answer unknown otherwise. Okay. Answer to a ground disjunctive query with this O operator is yes if the program entails at least one of these. Okay. No if program entails the negation of all of them. Unknown otherwise. Okay. And if we answer query of this form, saying a predicate and a RTN and variable of n, it will give all the objects so that program entail Q of these T objects. Okay. So let us look at another example here. Okay. Here we have a program, and this time this program have these variables. Okay. These variables x and qx, also it has these two. Okay, so here we have variables. So when we have variables, before computing the answer set, I have to ground this program. To ground this program, I have to replace all the variables with all the objects in our signature. Okay. Then one thing, when we are replacing these two x refers to the same variable. So the x in the rule 27 refers to the same variable. So if I plug object A to here, I have to plug A to qx also. But the variables in the rule 28 and 27 are not connected. Okay. So this one, x in the 28 time independent from the x in the 27. Okay, so I will assume we have only two objects in our signature. We'll assume it is given that A and B are the only objects here. Okay, so if I ground this program, I get this one. I get QA, RB, QA implies PA, QB implies PB by attaching A and B for first rule, and then attaching A and B for second rule, I get this. Not A, RA, not S, and RB, not SB. Okay. So now this program have answer RB and RB. Oh, sorry, I think I should have said QA. Right. Okay, RB and RA and QA. So, no, yeah, QB. Okay. Instead of that, this should be QA. Sorry. So it will include. Okay, I'll make this one. Sorry, I'll make this one. Yeah, I think I did a typo coming from this one to this one. This one should be a B. Sorry. Okay. This one should be a B. Okay. So this one RB and QB. Okay, so this is QB and this is RB. So I have to include those two facts in my answer set. Now, because I have QB in my answer set, I have to include PB, okay, into my answer set. But QA is not in my answer set, so I'm not going to include PA. Okay. Now I don't have RA in my answer set. So the body of not this one is satisfied by this set. So I have to include not SA. Okay. And I'm not going to include not SB because RB is in my answer set. Okay. So this is the answer set for this program, and program entails these literals. Okay. Now, if I ask the question about the query PA, I will answer here unknown because PA is not in my answer set. Also, not PA is not in my answer set. So I will remain unknown about the status of PA. Okay. Then if I ask PB, I will say yes because PB belongs to this answer set. Okay. And if I ask SA, I will answer no because SA is not SA is in my answer set. Okay. And if I ask SB, it will again answer unknown because SB is not in my answer set. Okay. So here I don't have PA or not PA in my answer set. Okay. We remain unknown about the status of PA. Okay. So we can add another rule to here, this type of rule. Okay. So here not px implies not px. Okay. So it's same as the previous program. I add this rule 29 additionally. Okay. I add this rule 29 additionally. What it does, it's make our answer set complete respect to all the objects of P. Okay. So our answer set will either contain PA or not PA, negation of PA. Okay, so here again I ground all the rules with A and B. Again, this thing should be B, sorry. Okay. Now my answer set should contain QB and RB. Okay, QB and RB, QB and RB. So because QB and RB there, I am including PB from this rule and not SA because I don't have RA in here. And because I have RB, I will not include not SB. Okay. Then PA is not in my set. Because of that, from this rule 46, this is the grounded version of the new rule. I included PA. And I'm not going to include PB because PB is in my answer set. Now you can see this answer set is complete with respect to P. That means for every object in our domain, at least it contains P of that object or negation of that object, negation of P of that object. Okay, see here PB is here and not PA is here. But if I look at RB, I don't know about the through RA. Okay, RA is not here. Also not RA is not here. Okay, so this program entails this one because we have only one answer set. So now for PA, it answers no, PB yes, SA no, and SB unknown. Okay, so this is called the completeness axiom. It will complete the answer set with respect to a given predicate. Okay. Now I will go to the formal semantics. Okay. Pair is literals of form, this form and this negation of a predicate and the classical negation of a predicate and this predicate uh, called contrary. Okay, set S of ground literals called consistent if it is contains no contrary literals. Okay. So then answer set we define in two parts. Okay. First part of answer set is for this type of rule where we don't have the classical negation. So for the first, we define answer set, how to get a formal computation of answer set here. Okay, so H satisfies all the rule of pi and S is minimal. Okay, that means there is no proper subset of H satisfying the rules of pi. Okay, so I will do a one example from this formal one example from this formal type. Again, if we look at this program, here I have to satisfy this rule 48. So I have to include one of them, not to satisfy. Let's say I include QA, then it satisfy this rule. And if I have QA, I have PA. Okay, like before, if I have QB, I have PA. So if I take now this answer set satisfy all the rules, no? Because it satisfies QB because no body is not there, so it trivially satisfies rule 50, and then 49 because it contains the head, and 48 because it contains one of them. Now, if I remove any of these literals from these sets, then they are not going to satisfy this program. So because of that, these are the minimal answer set satisfying the program. I can have again that PA and PA and PB with a sorry, QA and QB in answer set, then it's not minimal because I can remove one of them. Okay, so if I consider I have QA and QB and PA in my answer set. Now this answer set satisfies also all the rules but it is not minimal, because if I remove this subset of that, answer set satisfies all the rules. Okay, so it's not minimal. So this is why we take these two answer sets. They are the minimal answer set satisfying all the rules. Okay. Now when we have not test, we have to first compute answer set, and we can check whether that answer set is a first we have to come up with a set S, and then we can check whether the set S is a answer set of the program containing not S else. Okay, so for this what we do, we construct a new program pi x called the reduct of pi by following these two rules. Okay, so if I want to check whether S is an answer set, I have to remove all the rules containing not S, not L if L is an answer element of the S. Then I remove all the other premises containing not. Okay, so X is an answer set of pi, then S is an answer set of pi S. Okay, then if S is answer set of pi S, then we can say X is also answer set of pi. Okay, so here we have the previous program, this one, and I know informally this is my answer set, no, from using informal semantics. Now to check it formally, I have to construct the reduct of this, let's say this program is pi. So I have to compute the reduct of pi, a new program pi s. Okay. So if I look at PB is in this set. So according to that rules, I have to remove this rule from my new program. Okay. And PA is, then I have to remove all the other literals containing not. So I have to only remove this literal. So I keep the head, it becomes a fact now. Okay. So this is QA. And this rule I removed. I have the last rule also because it's not affected by that process. Okay. So this is my nuance program. It contains only two facts, and its answer set is what? QA and PB. Okay. So this is the new answer set of this one. It's same as this, no? So S is answer set of this new program. Therefore, it's also answer set of the old program. Okay. So this is how you will construct a formal answer checker for whether answer set is part of this formally. Okay. Now I will describe some examples where we use this, where we can use this program. Okay, I will give only simple program, and others I will go just what type of things we can do. So here we have this family. So here object of this family are John, Sam, Alice, and we have two variables X and Y in our signature. Then we have predicates. Here person is a predicate here, and John is a person, Sam is a person, Alice is a person. Also we know John is the father of Sam, Alice is a mother of Sam. Okay, then we can derive new rules saying X is a new predicate, X is a parent of Y if X is a father of Y, and X is a parent of Y if X is the mother of Y. Also X is the child of Y if Y is the parent of X. Okay, so if I have these rules, my program can answer queries like if I ask John, father of Sam, it will answer yes. Okay. Also, if I ask John is a parent of Sam, it will answer yes. Okay. So now Now think of a rule where this default knowledge, normally parents care about their children. John is a Sam's parents, therefore John cares about Sam. So if we give this normal rule if I give that information and this rule for a rational person, he will say that John cares about Sam. He will decide that John cares about Sam because normally parents care about their children. Okay. So that one we can include this rule like 9. So I'm saying X is caring. If X is the parent of Y, then X cares about his children. No, Y. If X is the parent of Y, X cares about Y. Okay. So here, now I can, if I ask the parent if I ask the program whether the John cares about Sam, it will answer yes because of this rule 9. Okay. But think that we learned that additionally to this, normally parents care about their children. We learned that John is an exception to this rule. Okay. He does not care about his children. Okay. So this new information can be represented by a rule like this. Okay. Child of X, X don't care about his children. John don't care about this children. I can include this rule. But now there is a problem because this rule with 10 is contradicting with rule 9 and my program will become inconsistent. So if I follow this pattern, I cannot represent this type of knowledge. Okay. So I can use not operator here to come out of that problem. Okay. I represent the normality rule like this. Okay. I say parent X cares about Y if not given, not cares. So here I'm saying if there is no information available, in general, we consider parents care about the children. Okay. So if I have this rule, now if I learn John don't care about his children, this one I can add as a strict rule. These are called default rules. Take rule like 9. So now here, if this program I ask whether John cares about Sam, it will answer no. Okay, but if I include another pair of parents and their child, if I ask those parents care about their children, it will answer yes. Okay, so this shows how we can use this not to handle this default notation, default knowledge. Okay, actually, it can be generalized for this rule. If I have normally element of class C have property P, it can be represented by a rule of this type. Okay. So, okay. This one, this abnormality condition we use to block a default, not without deciding the negation. If we want to block a default, I can use this abnormality condition and I have this px like here, not chaos like that one. I have not px. Additionally, we add a condition where we allow by activating this abnormality condition, we can stop this default being applied for specific items, but it will not go against it, like having not px. Okay. So this, if I have not px, it's called a strong objection to the default that will decide against the default like before. But if I do abnormality condition, activate abnormality condition, it will remain unknown about the situation. Okay. So you can, I only included the simple example because I took time to discuss about the semantics and the formal semantics. So there are a lot of examples you can cover using this abstract pattern this rule, you can apply it for a lot of real life arguing processors. Okay, so they use this default knowledge and construct lot of programs, and also it can be used to solve classical planning problems. Okay, so for example, let's say I have this table and I have these blocks on the table. Okay, I can put a uh, block on the table, or I can put a block on one of top of another block. So I can remove a block and put it a table, and I can take out block out of the table and put on top of a new block, or I can take a block and put that block on another tower. Okay, so in that situation, if I have this initial configuration, and if I want to go to another configuration, I can write a program which is capable of computing a plan, and it will give list of movements, how I can go from this configuration for the other configuration. Okay. Only thing that program cannot tell the minimum number of steps required. We have to give a number of steps. So if our number of steps are not enough, it will say that it's impossible to come up with a plan. And if we keep increasing the number of steps, as soon as we come to a step that is enough for, let's say 10 step is enough. Soon as I come to 10, it will give us a plan. And then if I use more step, unfortunately, then it come up with plans that require 12 step or 13 step. Then it will do some things that is not required to do, just maybe duplicate some movements or like that. Okay, I will not go over the program because it takes time, but this is one thing you can do with this normal logic. Also, you can use it for diagnosis systems. Okay, so think that I have this simple system, and when I close this switch S1, this coil get activated, and it will generate a maximum force and close the F2. So F2 is closed, this bulb will lit. Okay, so let's say there is an agent observing this system. He knows that S1, closing of S1 will cause to S2 to close and bulb to lit. Okay, also he knows there are two actions in nature that can occur and damage this system. It can burn the coil by if a surge occurs, it will burn the coil and it will damage the bulb. Okay, and if the break occurs, it will damage the bulb bonding. So in the beginning, agent knows this everything is in working condition. He can observe whether closing of switch 1 occurred, whether the closing of S2 occurred, and whether the bulb is lit. Okay. And he don't have any way to observe that conditions by nature. That is the break condition and the surge condition. So he know in the beginning, he know all the components are working, and then he observed that S1 switch is closed, and then S2 don't get closed or the bulb don't get lit. Let's say he observed that bulb don't get lit. Okay, then that agent can come up with a symptoms and check whether what is occurred, whether the surge occurred or the bulb occurred. We can use this programming to write a diagnostic program like that. Okay. So there are also some other applications where we can use this one to solving puzzles and things like that. When you do this program, we don't have to give an algorithm. We only need to define the problem. Okay. We don't have to. So even here, I'm giving just the definition of parent. Okay. It can automatically decide. Then it can automatically decide who are the parents. Okay. So I will stop my presentation here. If you have any questions, you can ask now. Okay. I just concentrated on this book. Okay, mostly these things are from this book. Okay, intelligent agent and answer set programming approach. I am trying to uh, improve a problem involving these default rules where we have conflicting defaults. Okay, I am currently trying to improve something regarding to this. Also, I am learning this one still. So if you have any questions, you can ask now.
Nadika, thanks
Oh,
for your presentation. I'm Chatura Rajapaksha.
okay, yeah,
Nadika, I just have a very general question actually.
yeah.
Now, as you think, what is the future of Prolog? I mean, in the field of AI, how is Prolog progressing
Okay.
now, as of now?
Yeah, this is a spin-off of answer. So the thing is, I'm also new to this research field.
Okay.
I know one company. When I was searching the web, I found out one company that is using this actually DLV. Okay, this is called answer set program. So it is a new branch of this, and
Right.
DLV is one solar. So I found one company using this research this components the DLV and this knowledge representation and logic things. It's a spin-off company from a university. I don't know actually how much practically these things are applicable, but I know for this is mainly Dr. Gelfand work I discussed today. So
Right.
he won award for most influential research in logic and logic programming for last 20 years. So he is well known and his work is kind of accepted. He has sort of citations and but
What's his
for the
name again, please? What is his name again?
Gelfand Michael. I'll go for it. Yeah, this Gelfand Michael Gelfand.
Okay, fine, thanks.
And,
Because I was just checking whether there are any equivalent libraries for logic programming in Python also, but apparently there's not much progress in Python community as well. That's why I wanted to know.
Okay, yeah. If you can email me, I can send a copy of the book and that company who's link up to the company who's using this. They say that they help with undergraduate students for their projects and stuff. So but I'm still studying this field, so I don't know how much applications this one have. When I was working with him, these ones are at theoretical level. There was
Right.
some interest for this one, but I don't know exactly how much they use it in with other code. I have seen one paper who's trying to use machine learning and these concepts together. Here they don't talk about mostly about theoretical background and how to represent knowledge. Like, yeah.
Thanks, sir. Thanks a lot, Nadi. Thank you very much. Appreciate it.
Yeah, welcome. Any other questions?
Yes, I'm Rasika here. Could it be used for this case-based reasoning? And it was like discussed few years ago, but recently I didn't hear about it, and I'm also not in this area.
Okay. Yeah, unfortunately, I don't know about case by reasoning. Are you suggesting something? We can check that, but I am not aware of the case by reasoning. I only know about this field and I'm studying about that field. So here if you are familiar, these are called declarative program. So we don't have to give an algorithm for these things. We only have to define like rules of the situation. Then it can come up with a solution. I think maybe Prolog is also like that. This called declarative programming. Maybe someone have a better knowledge on that than me. So for example, if we consider that 8 coins problem, where we have to place 8 coins on a chessboard, so they are not attacking each other. We only have to say that chessboard has 64 squares and coins cannot be on a rank or a pile. Then it can come up with all the positions by itself. So in these things, we only give the knowledge to the computer about the world using here. So they are interested in how to represent the knowledge using this language. And then, but we don't have to give an algorithm on how to argue. So I don't know whether it's helpful for what you asked or not.
Yes, thank you, Nadeek.
Okay.
And since there's no more questions, and also if you want that, we can directly write to Dr. Nadeek. Therefore, shall we wind up the session now?
Yeah, that's fine. Thank you for inviting.
Thank you very much
me
for
and
Dr. Nadeek coming and sharing your knowledge with us. And thank you for your participation also.
thank you for giving me the opportunity and taking time to join.
Good night, everyone.
Good night.